I think I have now been able, those who cannot join us here can now join the YouTube. It will direct you to YouTube. So, so please try to go there. You can now, those who cannot make it to this place can go to the YouTube. You will be accepted, you will be able to come in. So as we were discussing, so the course, because learning outcome, by the time you are through with the course objectives are this. I have given you the textbook. The textbooks is foundation of, please, can you, if you make noise, I will have to eject you from this place. So the ground rule is that you should remain. I'm going to remove this fellow. So as I was saying, having been able to allow people to go to the YouTube now, then the textbooks are as listed. And then the GET lecture, at the end of the lecture, we should be able to understand the basic electrical principle and abstract upon the electronic circuits. We should be able to use principles to analyze and design simple electronic circuits. Likewise, we will look at lumped circuit model. You should be able to use intuition to be able to get some solution for electrical circuit. And then you should be able to develop simple differential equation for describing circuits in electrical engineering, especially with regard to energy storage element. And then we should be able to take some measurement using multimeters, signal generator, and oscilloscope in the laboratory. These are the major aspects of the course that you are expected to be able to handle. Then the learning outcome, by the time you are concluding this particular course, you should have been able to handle or to understand a number of things, how to analyze resistive circuit, how to determine the time behavior of first and second order circuit. You should have been able to have ability to determine the frequency response of circuit and how to use op-amp model. To some extent, we will look at op-amp, introducing you to op-amp, and then how to use some of these things in the laboratory. And as from the material I gave to your class rep, our week one, we are going to, in the week two, we will look at series and parallel circuit, and so on like that, till we are through with the lecture by 16th of February next year. And then we will take our first quiz by 24th of January 2026, while our second quiz before exam begins will be taken on 21st of February 2026. So on the account of that, you must have been able to handle the major thing. Then we have some problem set, otherwise known as homework. So you are going to be using the textbook that we have been able to tell you that you will use it to solve problem based on these particular. You will take the exercises at the back of it so that you can be able to use it to submit. So some of you are not under the classroom environment. This is totally unacceptable. I think I need to remove this guy. So some of you, I think I told you that you must be in a classroom environment. for this lecture, you must be in classroom environment. You can't be taking lecture along the road, because I expect you to jot down your note, because I'm going to ask you for your note. Maybe I forgot to let you know this. You must have your note, which I will go through, you will submit, and I will look at those who have complete note. You need to be aware of this, please. So, materials on the lecture. I don't know if you have any question, you will have opportunity to ask. Any question based on the first day package.
Sir,
So,
hello, sir.
yeah,
Can you hear me, sir?
yes,
Would the slide for the classes will it be available after each classes?
it will not be available, because I can see that some of you are not very serious. How can you be receiving lecture along the road? You have to jot. I will take time and wait for you to take your jotting. So you must be in a classroom environment. Thank you, Odutola, for that question. There must be lecture
Okay,
note
sir.
for this course. There must be lecture note for this course. It's like a classroom environment. So if you are going to be part of this lecture, you will settle down in a place where there won't be any distraction, and then you will have your lecture notes by you, which you will be jotting as I am going from slide to slide. Thank you for that question. It's a very vital one.
Hello, sir. Sorry, sir.
Yeah,
Sir, will the exam for this course be CBT or written?
I can't give you that now. When we get there, we will discuss that.
All right, sir.
Yeah, thank you.
Yes.
However, our first test will be CBT. The first test will be CBT. That's quiz 1. Okay, so we want to proceed now to our first lecture for the semester. And then we are looking at the following: Introduction to Applied Electricity 1. We are going to be looking at what is the discipline of electrical engineering all about? What do we understand by lump circuit modeling? What is device law or laws? What are device laws? Current source, voltage source, and IV characteristics. We may not be able to finish this today, but we are just going to start it. So when you are talking of electrical engineering, the discipline of electrical engineering is very wide. As you can see on the slide above, you are free to draw, because I will wait for another 2-3 minutes for you to draw this. In engineering, generally, you have mathematics, you have engineering, and you have physical. So mathematical foundation is what you have been taught in science to some extent. And some of them we are still going to teach you. The engineering application, because our own area, engineering is all about is the ability to apply the knowledge of science to generate comfort for the humanity. I don't know whether you got that right. Engineering practice is the application of science fundamentals to generate comfort for humanity. That's all we do. We want to give comfort to everybody. And so we use the engineering, the science, basic science knowledge to generate applications that can make life easy for everyone. That's all we do. And you can see those arrows. The arrow from mathematical foundations, which is more of science foundations, and how it is able to lead to engineering applications. And from engineering application, you can see the physical foundation as well goes into it. So you have the mathematical foundation, which is network theory. logic theory, and system theory. That's basically the three things that we deal with in electrical engineering. And then you have the physical foundation, electromagnetics, solid state physics, and optics. And by the time this comes together, they are able to generate electrical engineering applications for power systems, electrical machines, analog electronics, digital electronics, computer system engineering, control systems engineering, communication systems engineering, as well as instrumentation system engineering. So you can see that for you to get any of these, you need the basic knowledge of science and you need to have knowledge of physics. So that is why physics people, they have to take this course alongside with other engineering departments. So you need the knowledge of mathematics and you need the knowledge of physics. Bringing the two together, you have electrical engineering. So the typical curriculum of an undergraduate electrical engineering student include the subject listed in the structure on the left side. Although the distinction between some of these subjects is not always clear-cut, the structure is sufficiently representative to serve the purpose of making students to appreciate the curriculum. It also presents the possible interconnection between the disciplines. So this is all that electrical engineering discipline is all about. So we want to move from that place to what do we mean by lumped circuit model? When we are talking, when you take any electrical cable, I don't have an electrical cable here, but I will use my biro as an example. Let's assume this is an electrical cable. The whole of this electrical cable, you may not be able, or let me use my cord, my computer cord as an example. The whole of this computer power cable, as you are looking at it, there are, for it to conduct electricity from the socket to my computer system, then there must be flow of current through this cable. However, at your level, we don't want to say that those parameters, that is the resistance, inductance, and capacitance in this cable, we don't want to say that they are distributed. So we try to say, let us gather all of them together. As long as this cable is, let's say from this my finger to the other finger, from the right hand finger to the left hand finger, let's say that's the total length that I want to use to power or to supply electricity from one point to another device. This particular length, the way we explain the elements, the electrical elements, what are the electrical elements? Called resistance, inductance, capacitance, voltage, and current. These are the major electrical elements. But let's take the elements within this particular cable, which is resistance, inductance, and capacitance. Though we cannot see where they are laid in this place, but at your level, we subject it to what we call lumped network analysis. Lumped network analysis. In other words, let's say this is the length of my electrical wire. We try to say the whole of resistance is here. Meanwhile, in real life, the whole of resistance is not here. We take another small space, we say the whole of reactance is here. And then we take another space, we say the whole of capacitance is here, just like I saw it in this diagram that you are seeing on your screen. But that is not the true representation. But at your level, that is what we will teach you. And that is what you should worry yourself about. So on the account of that, by bringing together all the circuit elements, we are calling it that we are lumping them together. That's where the word lumped network comes from. So the lumped network is saying that all the resistors, the way we pack it, the way we pack all the capacitance, the way we pack all the inductance. So that is what we mean by lumped network. In other words, we put the network together, believing that for easy of analysis for you at your level, we put all of them together. And even though elements are connected by wire lead, these wire leads are considered zero resistance. Thus, the number of simple elements with the set of connecting leads is referred to as lumped network. In advanced classes in electrical engineering, just like as I've said, a more difficult way to analyze involves distributed network. But at your level, we deal with lumped network. That's why we have what we call lumped circuit model. It's a circuit model that we take as being lumped together. So when we are considering lumped circuit, we must know that one of the most important common applications of this is the conservation of its charges. And it is a common experience as well that in a physics laboratory that we connect electrical components in form of resistor, capacitor, and inductance along with various current and voltage sources. This we do in order to predict the behavior of the physical circuit. However, a distinct engineering science called the circuit theory has been developed to model and analyze the physical system. So when we are looking at the lumped circuit model, we have the information like this. The key assumptions that we normally make in lumped circuit model are: one, lumped circuits are constructed from discrete lumped circuit elements. Number two, electrical and magnetic energy is stored or converted to other form of energy. Number three is that no time-varying magnetic field intersects any of these circuit loops. And finally, lump circuits are physically small. The time scale of interest are much greater than the time for an electrical disturbance. I'll give you 2 minutes to write this in your note because I need your note. So my 2 minutes is reading now.
Sir, please, can we use short note or it has to be higher education?
Whichever one, anyone can be used. Yeah, I'm listening to you. I'm hearing you.
Sir, please, if you want to go to this thing again, maybe for just reading purposes.
I can't hear you. I can't hear you
said I
clearly.
want to go, if you want to go through this course again, if you want to read for exam or test, what will you do about it when you say you're not dropping PDF or any lecture like that?
I can't hear you. Speak louder. Get closer to your mic.
Sir, I said, what if you want to read for exam or test, sir? How will you do it when you say you're not dropping lecture note or slides, sir?
Because you have to jot your note now. I want you to be forming your note. That's why I'm waiting now. I want you to be writing your note. It's not at your level that we give materials to you. You are entering into engineering. I can't give you material. You have to write with your own handwriting because I'm going to ask for those notes. You are going to submit these notes. Maybe you didn't listen when I was giving the ground rules. You are going to submit your note for assessment too. So don't think Somebody will give you slides. That's why I scroll down now and you are copying the note. So I think the 2 minutes has become 3 minutes. So I want to move on now. So still on typical on lump circuit model, we still have this more information. I tell you here that typical lump circuit elements include resistor, inductor, capacitor, voltage and current sources connected by the wire. I've explained this before. I just have to elaborate by providing the note. I said that it should be noted that lump circuit elements are models for the real physical components. We just model them for the real physical component. Although physical circuits are never exactly match the corresponding lump circuit, I have explained it by using my computer power cable. The power of the circuit theory is its ability to accurately predict the behavior of the physical circuit. In fact, their use is so prevalent and so accepted that we often forget the assumption inherent in the model. So whenever we are using lump circuit model, the assumption that we make, by the time we look at it, there is a very limited variance to the physical circuit that we are dealing with. Even for using lump circuit model, it doesn't really totally vary from the physical circuit by the time we do the normal analysis of this particular system. So I will give you 2 minutes to write this as well. And another thing is that even just like the last speaker spoke, even if you want to watch it again, it's on the YouTube. This lecture is being live streamed now, so that those of you who, because the Zoom link has capacity for 300 participants, but the YouTube, a number of you have gone there quite severally to go and check, and I see that close to 100 was there as at the last time, even though I was expecting more than that in that place, because this course is for 1,000 plus students. So as at now, it's only 52 that are watching live on that platform. So even if you have challenge with it now, you can always go back there and watch again for those who are asking me questions. But I'm not giving you liberty. That when you have done that, you have already concluded everything. No? Because by the time I ask for your note, you must have note that you will give to me that I will have to look at. So I want to believe that you are through with that. I want to move on with the lecture now. I want to move on now. So I said here that when the conservation of charge equation is applied to a lumped circuit element, the key lumped circuit assumption is that no electric field exists in the space. And if a system boundary is not pierced by the electric field line, then it is impossible to change the amount of net charge. And I said this is a consequence of Gauss' law, which study in physics and is always true for a lump circuit network. And we normally refer to this whenever we are dealing with Kirchhoff current law. So in the case then with the lump circuit model, we still have some other information as you have it here, which you may not necessarily have to write down. So when we are dealing with lump circuit model, this is the kind of situation that we are looking at. That the assumption of lump circuit is that the propagation time within the circuit are much smaller than the time variation of the electric circuit, or the electric quantity, when treating waves. The lump circuit assumption consider them propagating instantaneously within the circuit. So we have this as a lump circuit. Beyond this, I want to define, so that's all about lumped circuit. We are going to be practicalizing it very soon, or we are going to be putting our hands on it very soon. But before then, let me define some concept. That is some basic circuit concept. There are certain basic circuit concepts that you need to know, such as branch, node, loop, mesh. What do these things mean? Ideal source and the other form of sources. So intuitively, an ideal source is a source that can provide an arbitrary amount of energy. In other words, ideal sources can be divided into two: voltage sources and current sources. Let me give you 1 minute to write this. So these are the ideal sources.
Sir, sir, you said
Before you ask questions, you must raise up your hand, please. Don't interrupt the class. Let me see your hands raised up. Okay, Adam, what's the question?
well, sir, you said you want to give us 1 minute to write that down. You've already gone to the next slide, sir. Sir,
You
sir,
have
can you hear
many,
me?
what is happening there? This is not a normal classroom that you are in. Move to where there is no noise, please. And don't disturb the class. You know this thing is being recorded. And the people on the YouTube, you will be confusing them with whatever you are doing here. So I need you to really, really be very careful wherever you are going to. You can see that I'm giving my lecture where there is no interruption. It's not that I cannot say elsewhere, but we need total and absolute concentration. So please, if you must ask questions, make sure that you are in a place that there is no noise of any sort. Please, I'm pleading with you. If it happens again, such a fellow, I will remove him from the something so that you do not constitute a unnecessary distance to us. So when we are dealing with the basic circuit concept, now the ideal source is an electric device that generates, as I have told you before, prescribed voltage. The ability of an ideal source, voltage source to generate its output is not affected by the current it was supplied. So when we call a particular source an ideal source, it means that it has ability to supply any prescribed voltage that you want it to supply. And the current, current and voltage, they are always relatable, or you have a relationship between them. So on the account of that, if you have a very an ideal source, your current may not have much influence on it, even though in the practical sense of it, voltage and current are related. In other words, when voltage is high, current must be small. When current is high, voltage must be small. That's our relationship of these two parameters. But in this place, the output of your voltage is not affected by the current status of that particular system, circuit. So in that case, you have what the diagrams, those three diagrams there. I know the question that the young man wants to ask about lumped circuit model. The lumped circuit, if you look at the diagram here, you can see the lumped circuit. The lumped circuit is the one the lumped circuit model is the one that we lump together like a rectangle. That's where you put all your circuit elements. That is your resistance, inductance, capacitance, depending on the one you need or the one you are looking at. But when you are talking of ideal source, you can see the general symbol for an ideal source as represented by Vs of t. Vs means ideal voltage source, and it has plus and minus at the both terminals. You can represent it in, that is for AC. AC, you will have a bubble. When you are representing voltage in AC, you will have it as a bubble. But when you are representing for DC, you will have the shorter terminal and the shorter plate and longer plate. The longer plate will be positive, the shorter plate will be negative. That's what you are seeing in the second circuit, where you have longer plate on top towards your top, towards your left-hand side of the second circuit. And then you have the shorter plate, the longer plate, the shorter plate. And the shorter plate is identified as negative. The longer plate is identified as positive. So whenever you see this kind of longer plate, shorter plate, longer plate, shorter plate, it gives you the impression that you are dealing with DC. Another name for DC is direct current. So you are dealing with direct current voltage source, and it is called ideal battery. When you call something ideal, it means that just like as I've explained, your rule of voltage and current interaction or their proportionality relationship is not totally followed in this place. That's what we mean by being an ideal. So you can have ideal situation and you can have practical real life situation. Then, if you look at the third circuit, if you look at the third circuit, you will see again a situation there. And what is the situation you see there? You will see that the voltage source has a kind of wave inside it between the positive and negative terminal. You see the waveform that is there. That waveform inside that bubble is telling us that it is AC. Just like you have shorter plate, longer plate, shorter plate, longer plate. AC as well can be represented with that wave that you are seeing inside it. And then You may ask me, what of the positive, negative on the other side, which is where you have the tag circuit written? That is where you are affecting or you are tapping your load or your output. So it is your output terminal. Whatever you put in that place stands for your output. So it is your output terminal that you are having in that particular place. And then that one we so that one, if you look at the equation there, you can see the voltage source. The equation has a cos omega t. Can you see that? V of s is equal to capital V cos omega t. That is because you are dealing now with a sinusoidal wave source. Note that by convention, the direction of positive current flow out of a voltage source is out of the positive terminal. Please take note of that note that I put in blue. Take note of that note that I put in blue. Whichever place that you take as your positive is where your current flows out from. And you will need this when we get to circuit analysis with Kirchhoff current law, Kirchhoff voltage law, Norton analysis, Norton theorem, and the rest of them, the Venice. We will need this particular convention seriously. So please take note of that in blue. But the convention is that the current flows out from the positive terminal of the voltage source. So by now you should have finished copying the note. I want to move to the next slide. So we still have the further explanation of this, but now we are dealing with current source. You can see the current source. In this case, we don't have, the bubble is still there, but we don't have positive or negative inside that bubble. If you look at it, we have an arrow pointing upward. So that's the voltage source. So I wrote here that an ideal current source is a device that can generate, I said voltage is a current source rather. With the arrow stands for current flow. Positive, negative stands for positive side of the battery and this negative side of the battery, meaning that there is a voltage in between the two of them. Voltage drop or voltage growth in between the two of them. Now, when you have an arrow, it is showing you that that is the current, and it's pointing in the direction of the flow of the current. So for an ideal current source, as a device, it can generate a prescribed current independent of the circuit to which it is connected. So it can generate the current that you are expecting it to generate independent of the circuit. To do so, it must be able to generate an arbitrary voltage across its terminals. An ideal current source provides a prescribed current to any circuit connected to it. The voltage generated by the source is determined by the circuit connected to it. So take note of that. It can generate any current for the circuit. So looking at it, the same uppercase and lowercase conversion is used for voltage sources as well as for current sources. So SBS stands for source. The I capital and I small letter, they stand for the current. And your circuit there is the output terminal. In a more precise way, we have this. So we have two types of sources. We have dependent sources and independent sources. And in this place now, you have the independent sources. The independent sources or the ideal source is the source that does not depend. The capacity, the value does not depend on anything, but other parameters may depend on it. You need to know that. So when we say, look at the voltage, positive and negative inside that bubble, we are talking of Vs as ideal voltage source, and we call it independent voltage source. We will get to when you will need it. Then V equals to Vs for all I. For all I. That's what we have by the right-hand side of that independent voltage source. That's the mathematical expression there. That V with cross, horizontal cross, means for all I. And I there stands for current. And if you look at your right-hand side, you see the ideal current source as well, which we call independent current source. In this case, source current or source current is equal to I. So take note of that. These are examples of ideal sources of an electrical circuit. Then we have another information that I need to pass, and it has to do with dependent. We have looked at independent. Remember, here we look at independent sources. And then that is the ideal sources. Then you have the dependent sources, which is what we call the controlled sources. It can be in voltage, it can be in current. So when you have that kind of information, what do we mean by this? The source described so far have the capacity of generating prescribed voltage or current independent of any other element within the circuit. I have told you this before. So they are termed independent sources or ideal sources. There exists a number of, or a category of sources whose output is a function of the other voltage or current in the same circuit. So when you have this kind of situation, we call it dependent sources or controlled sources. So for a control or dependent sources, they are always represented by a diamond symbol. If you look at the diagram I have under here, you will see the diamond symbol. But for the voltage source, you will have positive and negative inside that diamond symbol. And for the current source, you will have the current arrow or symbol inside that diamond symbol. So when you have the voltage independent source, or rather dependent source, if you have voltage dependent source, we have two types of them. It can either be voltage control voltage source, that is voltage control voltage source, or voltage control current source. I'm going to discuss this further. And you can have two types of current as well, current control voltage source and current control current source. And their relationship is mathematically expressed in that table. For voltage control voltage source, you have Vs equal to micro or mu V of X. Where mu is the relationship between the two of them. Then for the current control current voltage source, you have the Vs equal to Ris. The same thing with Is, you have GVs, which is more like a conductance. We will explain some of these by the time we get to other slides. And then you have the Is to be equal to beta Ix. So you can see all those symbols that we use, those Greek symbols that we use, they are for us to differentiate from one to the other. It's not that it is a general form for it, but we generate that for us to tell you that there is a relationship in terms of a constant. So all those mu, r, g, and beta, they are relationship. I think I will have to stop here today so that you can digest what I have given to you. I don't want to rush you in such a way that you will not be overwhelmed by what we are to do. So next week, we will continue from this particular space. Any questions still? Any question, please?
Excuse me, sir.
Go on.
For the notes, do we have to write it like exactly, or we can like write it in our own way?
You can write it in your own way. The way it can even be the way I was giving you the lecture, that you were taking your own note and you are just looking at the slide to bring in some other things to it.
Okay, sir.
It's not a verbatim. I'm not asking you for a verbatim note. Once you understand what you are expected to do, so that I can prepare you for your exam, and you can make use of it as reference material later in future. That's all I am looking forward to. Any other question?
Excuse me, sir.
Go on.
For some of us that are using this 10 in one note, where we have to compile all other courses in one big note, hope that is accepted, or we have to like get a separate note for it.
No, I may not ask you to get a separate note, but you can divide your note now. You know,
Yes.
some of you are using this eight in one. You
Yes,
can
sir.
just say GET201, just leave it in one place. When I ask you to bring it, it may be department by department that you'll be bringing it. So
Okay,
I
sir.
will then, so that's not a big deal. I'm not going to
Yes.
keep your note with me. I understand what you are saying, so that when you need your note, you don't begin to look around for, when you need to read other notes, so that I don't keep your note with me. Don't worry. It will not get to that.
Thank you, sir.
Yeah.
Thank you, sir.
So we meet next week again. However, please go and download the textbooks. And if you cannot download, I have a downloaded copy. Your class rep may reach out to me so that I can share it with you. But I don't know whether I can go straight away into this platform. But maybe next lecture I will try to experiment on it. But one way or the other, I know you can do better work even than me when it comes to getting this material. So you can go ahead and generate the material online and see. But if you can't download it, then get back to me.
Thank you, sir.
Okay, so on this note, I think the lecture, we call it a day for the lecture. See you next week.
Well, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir. Goodbye, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Bye.